We are now moving on to Chapter 2. Chapter 2 is all about the ozone layer. In this one, we're going to learn why we need to protect the ozone layer. We're going to compare and contrast it between the ozone in the atmosphere and the ozone we actually breathe. And we're going to discuss why the ozone layer is actually getting smaller and the hole is getting bigger. And finally, what we are able to do to help. Oxygen comes in two different forms. It comes in O2 and O3. O3 is the ozone. O2 is the oxygen that we breathe. Notice that's the exact same element, but it's a different quantity. One has 2, one has 3. Well, oxygen absorbs energy from the sun. And then when it does that, these bonds break and rearrange to form O3. The absorption of that energy is called endothermic, and we're going to talk about that later on. Ozone is an allotropic form of oxygen. An allotrope are two or more different forms of the same element, but their properties are really different because their structures are different. O2 and O3 are both oxygen, but they're two different forms of oxygen. Just like graphite and diamonds are both considered carbon, but they're completely different. I would not want a graphite ring. I'd rather have a diamond ring. The ozone layer that we're concerned about is in the stratosphere. It's right here in the stratosphere. The ozone that is actually really harmful to us is down here at the sea level. That's the ozone that we're actually breathing. This is the layer right above where the jet planes fly. So when we fly, we're actually flying below the ozone layer. This graph shows how the concentration of ozone changes as you go up into the atmosphere. Notice that there's a fair amount of ozone in the troposphere, which is where we're breathing, and it can be hazardous to us. However, it is the greatest in the lower level of the stratosphere right here. This is important because it absorbs some of the sun's UV radiation. Now let's reflect more upon the oxygen as an element. In order to do that, we need to know a little bit more about what makes up an element. An element is the smallest unit of an atom is the smallest unit of an element. There are hundreds of particles that make up an atom, but we're going to focus on the three main ones: protons, neutrons, and electrons. Protons have a positive 1 charge, while electrons have a negative 1 charge. Neutrons don't have a charge at all. These three particles will allow us to predict reactivity of the atoms. The atomic number, which is written on the periodic table, is the number of protons. Since protons are in the center and protons are positive, that also tells us the charge of the nucleus. But if an atom is neutral, meaning that there's no charge, the positive of the protons and the negative of the electrons cancel out, which means this can also tell us how many electrons there are. Officially, it tells us the number of protons, but if it's neutral, it can tell us the number of electrons. And the electrons are what actually determines its reactivity. Let's move down to this mass number on the next slide. The other number on the periodic table is the atomic mass. The atomic mass is the average of all the isotopes in an element. And isotopes are atoms of an element that are exactly identical with one exception: the number of neutrons. Remember, neutrons are the ones without a charge. Therefore, the only thing that changes is the mass. This is why the average of the masses are taken. So this is the average. It's only the mass number if it's for a specific isotope. When we average all these together, we get the atomic mass, which is on the periodic table. There's one thing that is different that most people are not used to. They take the relative abundance into consideration. This means that they consider which isotope is more common. If a specific isotope of an atom is more common than another, this is added to the calculation. Therefore, the mass on the periodic table is the closest to the isotope that is the most common. For instance, if we looked on the periodic table, we would notice that carbon is 12.01. Carbon 12 is the most common. Therefore, the average mass is actually closest to the one that's the most common, rather than just taking an average of all three of the isotopes. Let's talk about the valence electrons, because they're the ones who are actually doing the reacting. Of all the electrons in an atom, the valence electrons are the most important. So when we're looking at the periodic table, the group number that it's in determines, or tells you, not really determines because that's how they got put in there, tells you how many valence electrons there are. The valence electrons are the outermost energy, so they're the ones that are furthest away from the center. The most important of these electrons are valence electrons. These are the electrons that are on the outside and the furthest away from the center, or the nucleus of the atom. These are the electrons that are actually reacting. You identify these electrons by the family or group in which they are in. You may remember that we stated that groups and families are the vertical rows and they react similarly. This is because the valence electrons are the same. Let's take a look at the structure of water and how we can determine the shape by analyzing the periodic table. Water is H2O, meaning that we have 2 hydrogens and 1 oxygen. The invisible number there is a 1. If we look on the periodic table, here's hydrogen, here's oxygen. We can see that hydrogen has 1 valence electron, and because oxygen is in row 6A, it has 6 valence electrons. So that means hydrogen has 1 dot each because it has 1 valence electron. Oxygen has 6 dots, 2, 3, 4, 5, 6, because it's in the 6th row. Ordinarily, the single electrons come together to make a bond. This doesn't happen 100% of the time, but it does happen most of the time. And this is how atoms combine to form a molecule. So there's 6 valence electrons in an oxygen, 1 valence electron in a hydrogen. And that's how we get this structure. These are called bonding pairs because these two pair up. And this is called a lone pair because they're all alone. Those 2 electrons don't actually get shared. Atoms will typically react or combine to have all the electrons paired up. Once the atoms have done that, they are more like the noble gases, which are on the far right of the periodic table. These all have paired electrons. You notice that they have the number 8 up there. When we count out the electrons, that means that there's 8. Go one at a time first, and then we pair it up. And so all their electrons are paired up. So let's go back to this slide. We can see that the electrons are all now paired up. These 2 were already paired, and now these 2 are a pair, and these 2 are a pair. This is how we know the molecule is stable. Sometimes to make the atoms be all paired, multiple bonds have to be used. For instance, oxygen, if oxygen wants to bond to itself, it has 2 single electrons each. Therefore, it has to bond twice. Carbon has 4 single electrons because it's in the 4th row, so it looks like this. So therefore, it needs 4 bonds to be stable. In this example, we have 4 electrons, and we still have 2 hydrogens out here, both with 1 electron. Those pair up, but we have these 3 single ones, so they stretch across to form a triple bond. If a multiple bond is involved, sometimes these bonds can be moved around. As a result, it forms a resonance bond. This is when we can put the double bond in several different locations. This actually becomes really important with ozone, as we will see momentarily. So if we see here, an oxygen bond has a double bond here, but we could have also drawn it here, and we could have also drawn it here. It's the same structure all 3 times, but that double bond moved from one location to the other. Ozone, this is the structure of ozone. Notice that there are 3 oxygen atoms. That's how we get the structure O3. Unlike the oxygen-oxygen double bond that we saw on the previous screen, that looks like this, there is 1 double bond and 1 single bond. Here's a double bond, here's a single bond. Notice also that there are a few different ways that we can write this same compound. So we can write the double bond on this side, or we can write it on the left side. We could even make it into a triangle. This means that the bond is in ozone are between single and double bonds. They're not quite a single and they're not quite a double. They're in between. This also means that they're stronger than a single bond but weaker than a double bond. So this is actually stronger than this. That's why it needs to absorb energy in order to break it down to form the ozone. In the next section of chapter 2, we're going to discuss how the energy is absorbed from the sun.